This was a collaborative work between different people and different institutions, as you can see on the slide. And I will briefly introduce to you ferroelectrics. I will talk about experimental setup, sample preparation, and which are, in my opinion, the major limitations associated with in-situ biasing on ferroelectrics. And further, I will show you some experimental results which have been published in Applied Physics Letters and Nanoletters. So a ferroelectric is a material which exhibits a spontaneous polarization even in the absence of electric field, and this spontaneous polarization can be flipped. Moreover, ferroelectrics are a class of pyroelectrics and piezoelectrics, which open up a wide range of possible applications from multilayer ceramic capacitor, ferroelectric random access memories, or sensors. And just to take a very simple example, in a smartphone, there are hundreds to 1,000 ferroelectric active elements, mostly in multilayer ceramic capacitors, but also in sensors, for instance, in microphones, pyroelectric sensors for face recognition, or piezoelectric sensors, for example, in auto adjust of the screen orientation. And at the local scales, ferroelectrics are associated with this idea of order. But this time the order is at nanoscale, so we cannot see it with our naked eye, but we need an electron microscope. And there are regions where the polarization points in a specific direction, and these regions are called domains. And in between, there is an interface. So a transition region, which is called the domain wall. Domain walls are very small features. They can only be a few units cell wide. However, you will see we are very interested in domain walls because it's where the order breaks. If we apply electric field to a ferroelectric, domain walls will move and the domain structure will reorganize as a consequence of the dipole moments trying to orient with the field. And there is a critical field called coercive field, for which the majority of dipole moments are oriented. The movement of domain walls and the response of the domains is responsible for the majority of non-linearities in the system, which in return give functionality to the material. And so what I do is I look at the domains and domain wall dynamic and how do they interact with other interfaces. As I mentioned before, I do this because their nanoscale response is directly related to their functionality. Just to give you an example, the domain wall dynamic has been shown to contribute up to 80% of the total macroscopic scale. And also, domain walls are atomic features which are potentially dynamic, and this is very attractive from the point of view of applications. And a relatively new paradigm has opened up, which is called domain wall nanoelectronics. And I do this by using a high resolution scanning transmission electron microscopy coupled with the in-situ biasing capabilities. I mostly use the protochip fusion holder and the focus ion beam optimized chip. And the focus ion beam optimized chip is a great development because there is no membrane, so there is just a notch between two electrodes, and we can place the specimen in the form of a microcapacitor between the two electrodes. So the goal is that at the end of the focus ion beam preparation, we have a sample which is thin enough so we can reach high resolution in the TEM, but also that it still maintains its, let's say, electrical integrity. And I think for this reason, ferroelectrics are a little bit more difficult materials because we don't just want to apply voltage and have a current flowing, but we want the specimen to behave as a capacitor. And we show by finite element modeling that the geometry and the thinning of the sample is very important, and it will change the electrical distribution. And of course, there are also other details to mention. For instance, even the platinum layer on top can bend the electric field lines. And I like to acknowledge that now there is a good record of publications which give different tricks and tips on how to prepare a successful specimen for in-situ biasing. But for the case of ferroelectrics, I think leakage currents are still an issue. As I mentioned before, ferroelectrics are highly insulating materials. So anything that is a little bit more conductive will be a leakage path. And here I have in mind the amorphous layer on top of the sample, which is a direct consequence of focus ion beam preparation. And on top of that, it's known now that ferroelectrics that are very thin will switch at higher fields because of pinning on surfaces. And what can happen is that we have a sample which will break down before switching takes place. And if you work with ferroelectrics, you will notice probably in my next slides that the behavior is mostly a behavior of a ferroelectric in so-called low electric field, so a subcoercive field regime. And this is partially a limitation of the sample preparation. However, it comes also with a positive side, which is that in low electric fields, we have more short-range phenomena, so it's easier to follow them, and also they are a little bit slower, so we can bring them down to the time resolution of the microscope. And next, I will show you the evolution under electric field of the domain structure in sodium-potassium niobate single crystal. And this is a specimen of potassium-sodium niobate, where it's very common to find these irregular features, which we believe they are non-edge-on domain walls. But looking closely, at local scales, we also have other type of domains, such as this comb of needles. And the needle-like domain walls are a very common morphology in many other materials, not only KNN. So when we apply electric field, the non-edge-on domain walls do not respond. However, the needle-like domains have a high mobility. You can see that the domain structure completely changes from 0 volts to plus 55 volts. So let's have a closer look on how the switching takes place at the nanoscale. Here we have 3 different types of domains, and for simplicity, I color them. The red domains, domains that are perpendicular to the red ones, which I colored them in blue, and the gray matrix. And on the plus polarity, when we apply electric field, the needles start growing from the tip in a forward motion until they meet an obstacle. And this obstacle can be, for instance, another domain wall, and then they start growing sideways. And this is a very nice example of the nucleation and growth classical model. However, on the negative polarity, we have a little bit of a different behavior. If before the red domains were growing, now they are, of course, shrinking when we flip the electric field, and the blue domains are growing. But they grow in forward motion only until a certain electric field, after which we have a sudden splitting into nanodomains. And these nanodomains are very unstable. In fact, the process is completely reversible. You can see that when we switch off the field, there is a complete back switching. And we believe that this happens due to stress accumulation. And other interesting observations is that we have nucleation from the edge of the sample. This shows how important are interfaces and surfaces in a microcapacitor. And also around the non-edge domain wall, we have random pinning of an area about 300 square nanometers, irregardless of the direction of the polarization or the direction of the electric field. And so if one will plot the relative coverage of one domain as a function of voltage, what we get is something that resembles a macroscopic hysteresis loop because the coverage is proportional to the polarization. And looking closely, there are different steps in this hysteresis loop. They are known in macroscopic measurements as Barkhausen or crackling noise. And in this case, we could directly associate them to soft pinning events of when 2 needle-like tips that are perpendicular meet. And so to conclude this part, when we have a very complex different domain structure, we will also have a complex switching, and we could show different individual switching events, such as reversible splitting into nanodomains, but also pinning, hard long-range pinning, but also soft pinning events like tip-to-tip interaction, which are responsible for cracking noise. And in the next slides, I will show you one study published in Nanoletters, which shows the interaction of one single domain wall at the atomic scale with electric field. And the material was rhombohedral bismuth ferrite single crystal, which has quite an ordered domain structure. It's common to see these lamellar-like domains and inside the zigzag domain walls. When electric field is applied, at least within the range of electric fields that we applied, the lamellar ones are pinned on, and we prove that they are pinned on crystallographic defects, but I'm not showing that here. And the zigzag domain walls are highly, highly mobile. However, you can see that even if all of them have the same morphology and they are of the same type, there are some regions in the sample which respond quicker and some that seem to respond slower. And this is because the effective local electric field does depend on many other factors, not only on the external electric field. And what often happens is that we don't have a long-range movement of the wall, but we just smear the contrast. And this, for us, was an indication that we do not switch the polarization necessary, but we change the property of the wall. And this was already quite interesting. So the next step was to look at one single domain wall at the atomic scale and see what happens when we apply electric field. So this is a not charged 180 domain wall, and this darker contrast in the middle of the atomic resolution image marks the initial position of the wall. And when we apply electric field, we actually didn't know what to expect. But what we saw is that we cannot get rid of this contrast, but it just smears around. And we thought that we don't have a switching, but that we only maybe change the structure of the wall. However, when we looked at the atomic displacements, which is a way of mapping polarization, we saw that we actually had the switching, and this switching is in accordance to the direction of the electric field, and it was true for more than one cycle. So this result was quite intriguing because this enhanced contrast in bright field images is usually taken as a landmark of the position of the wall. But here we show that when we apply electric field, the strain and the physical position of the wall can decouple. And we propose a hypothesis for it, which is that we have defects that segregate and which are immobile, and they stay at the initial position of the wall, even if the physical position of the wall moves. In bismuth ferrite, it's common to have segregation of different type of point charge defects, such as iron 4+. With ELs, we proved that we do not have any change in the oxidation state, so no iron 4+. In terms of bismuth vacancies, if any, we believe they do not segregate in high amount because we see no considerable intensity drop in the bismuth atomic columns. However, we consistently saw that we have a lower oxygen edge from ELs. Okay, and then if we look just at the tip of the zigzag domain wall, the tip is strongly charged. We saw that with electric field we have a little bit more pinning, but we could induce some asymmetry in the domain wall plane. And this kind of asymmetry has been previously reported for this kind of morphology at the nanoscale, but the atomic scale implication have not been shown. Here we show that we also have change in the magnitude of the polarization and also change in the direction. And this comes with other atomic scale implications, such as we do have different strain when electric field is applied, so we can redistribute the strain. at a very local scale, and as a consequence of the fact that we change the plane of the wall, but also the magnitude of the polarization, we change the amount of bound charges. And potentially we also have redistribution of bismuth vacancies. And so to conclude this part, we observe the interaction between electric field and one single domain wall at the atomic scale with atomic resolution under electric field. For the midsection of the zigzag domain walls, we show that the change in the position of the wall did not follow the position of the strain field. And our hypothesis is that this is due to immobile oxygen vacancy segregation. And for the charge tip of the zigzag domain wall, we show that it pinned, but very locally we can, with electric field, induce different strain and bound charge redistribution. So with this, I would like to thank Protochip for giving me the opportunity to present my work. And I acknowledge that maybe I didn't have time to explain everything. So if you have any other questions, please reach me at this email address. And thank you very much for your attention.